Delivery Systems, Part 1. Delivery systems are the most expensive component in a nuclear arsenal. In this lecture, we're going to explore different delivery systems and some of the mathematics behind it. We're going to look at different ways to launch and to target nuclear warheads. The weapons on this slide are German weapons. In the top left, you can see an A4 mobile launching site. The A4 was termed a V2 by the Western Allies, so it's the more common name. All German V2 launching sites were mobile. They were mobile because they were trying to avoid Allied bombing. So it meant they would be taken to a site. They had liquid fuel, so they had to be fueled, which would take a few minutes. And then they would be fired, and the main vehicles would then move to another location. Now, some argued that this missile program was a giant detriment to the German war cause. At the time that these missiles were being used, 50% of the explosives used by the German military was being used by this program alone. So it actually shortened the war by denying resources to the military. Hitler's promise of a miracle weapon to end the war was essentially this device. But they were far less effective, as we learned earlier, just because strategic bombing was far less effective. So the Germans manufactured 3,172 V2 rockets, which is the rocket that you see here in almost all of the pictures except for the glide bomb on the bottom left. Each of these cost 50% as much as a bomber. Now, as a general rule, bombers are much more cost effective than rockets. A rocket is fired and then it doesn't come back. A bomber can come back and then can relaunch the same sortie. A bomber can have different payloads. It can be targeted against ships, against infantry, against airfields, and it can have different types of payloads for different types of targets. Furthermore, humans who fly the bombers can be trained to deal with different kinds of targets. A missile like this is really only useful for an attack in a general area because it's not that accurate, so it'll come down on a city or a port facility. Whereas a bomber can hit a specific bridge or building or moving enemy target. Now the V1 cruise missile that you can see in the bottom left corner, the Germans built 23,172 of these. They used a pulse aircraft engine, and they would glide to a certain target, and then they had an internal gyro that would then cut the engine and cause the bomb to drop and glide in. It would glide in very slowly, and it could be seen, and aircraft would often fly next to them and try to knock them out of the sky by tapping their wings, or they could be shot down, since they flew at the speed of an aircraft. The V2 or A4 rockets came in faster than the speed of sound. So there was an enormous explosion, and then after that, you heard the flight of the rocket and you heard the detonation. Now this V1 at the bottom cost only 2% of a two-engine bomber. It was far more cost effective. So in terms of cost effectiveness, the V2 rocket was not cost effective. It was very useful to deliver a nuclear warhead, but Germany didn't have a nuclear warhead. And as far as Hitler's promise of a miracle weapon that would severely disrupt the Allied invasion, it didn't work. They were targeted on London. They were targeted on the port of Antwerp in order to disrupt Allied supplies, but they ultimately didn't work. Now these other V2s that you see here, you can see the V2. Let's see which is which. We can see the V2 in the center top. That's a Chinese V2. The Soviets obtained some V2s and handed them over to their allies. On the bottom center, we can see a V2 being tested by the Americans. On the bottom left, bottom right, we can see a V2 that was deployed by the French. And the V2 in the center left is clearly a German setup. So let's take a look at different system types. Nuclear weapons can be delivered in any one of 6 ways. The first way are missiles. The largest of these is the ICBM, the Intercontinental Ballistic Missile. Their flight time is about 30 minutes to 45 minutes between the US and the Soviet Union or vice versa, and they'd be flying over Canada. In this particular picture, you can see depicted a US Peacekeeper ICBM. These missiles are no longer in operation. Their common name is MX because that was the main name that came out in journalistic reports when there were arguments about how useful the missile was. It was cost effective, very sophisticated, very heavy, but ultimately it was pulled out of operation shortly after the end of the Cold War. On the left you see a MIRVed warhead. MIRVed is Multiple Independently Targeted Reentry Vehicle. Those are warheads that are sitting on top of a bus. It sits on the top of the missile, so it allows a missile to carry multiple warheads. And in this case, you can see that that warhead is actually what I suspect is a Peacekeeper or an MX missile. Is that bus will maneuver left or right as it's coming into the atmosphere and direct the other warheads ballistically. Now, a ballistic missile means the missile follows a ballistic path. It basically follows a kinetic path. The bus doesn't. The bus can maneuver. And some of the warheads are actually decoys. And so they're meant to absorb incoming anti-missile missiles. Now, the ICBM is the largest missile, but not the largest missile in theory. The largest missile in theory could be a missile designed against anti-satellite operations, which are in deep orbit around Earth. And we could, also think of one of those types of missiles being used to shoot down an asteroid. These are the deployments of the ICBMs in the Soviet Union. So these are the missiles that would be fired against the US. Some of these missiles had shorter ranges and would be fired locally, like the SS-4 and the SS-5. Of particular interest is the SS-18 fields. The SS-18 is still deployed by Russia. It's the largest missile they deploy. It was a missile that was built in the Ukraine, so none are being added. And it has 6 to 10 megaton range warheads. It's a very powerful system. Most of these missiles are gone because the Soviet Union's collapsed, and a lot of these missile fields are in now independent countries that don't want the missiles there, like Kazakhstan and Ukraine, that gave up the presence of missiles in their territory. This is the location of the 3 US ICBM fields. The fields today are equipped with Minuteman III missiles. They're older than the Peacekeeper missile, but they were kept because they're a standard model, easily upgraded. They're a smaller warhead. So you've got Maelstrom, Minot, and F.E. Warren base. All of the individual silos are known, and there are websites where you can go where it'll show you the Google view of these silos. Each of the silos consists of a very small complex that's fenced off. These are located across farmer fields. So they're right next to farmer fields. So it's relatively difficult to infiltrate. The farmers will see you and probably call the local police. You'll see that Minot Air Force Base has a couple of silos that are abutted right up next to the Canadian border. Minot Air Force Base also has bombers. Now these ICBM fields are located north, so they can fire quickly against the Soviet Union, but they're also located on the interior, so they're not easily destroyed by Soviet submarine nuclear weapons launches that would be launched in the opening phases of a nuclear attack. You can see the bomber bases as well, Whiteman Air Force Base and Barksdale Air Force Base. They're farther away to give the U.S. more time to launch the bombers into the air. And you can see the strategic submarine bases at Kings Bay, Georgia, and at Silverdale in Washington. And that's where you've got these submarines that go, the SSBMs that go underwater for several months at a time. I made this. This is a representation of the different bases in China and the missile brigades that are associated with them. This changes quite frequently. China is not currently engaged in a massive buildup of missiles. It seems to be very confident with the size of the arsenal it has, but that could change in the future. The Soviet Union went from almost no missiles at the time of the Cuban Missile Crisis, no ICBMs that could go to other continents, to by the end of the 1960s, less than 10 years later, it had 1,000 ICBMs. And by the end of the 1970s, it had 1,300 ICBMs. So if a country's committed, they can manufacture huge numbers of missiles and warheads to go along with them. This is actually U.S. Malmstrom Air Force Base at Great Falls, Missouri, with the layout of the different silo sites. So they're very dispersed and very spread out, but they're visible. You can go see them. In the event of a nuclear war between the U.S. and the Soviet Union, obviously it would have occurred over the North Pole. Now, we've never had a consistent all-weather launch of rockets over the North Pole, particularly during an aurora borealis. So it's very hard to know what effect it's going to have on accuracy, but I think the scientists are confident enough that it won't really matter that much, especially if they're following a ballistic or kinetic path. They're just going to go where gravity and inertia is going to land them. This exchange would take between 30 minutes and 45 minutes, and it's not inevitable, but those that operate the missiles would never want to have their missiles destroyed in the silo on the ground, and so they spent a lot of time practicing launching quickly. So even though we'll see later it's not necessary to launch missiles quickly, they're trained to launch them quickly. These are the different missile test ranges for countries, including France, the US, Soviet Union, and China, and the general regions where they fly these. And these other countries have different ships to monitor these launches. The Soviets had a ship called the Yuri Gagarin, which was sadly eventually scrapped and used in a very poor Hollywood B-movie. But in its day, it had all these satellite communications and radars, and it would go into the Pacific and track U.S. missile launches. The U.S. had the Judy Cobra, which is a ship with powerful radars, and the Americans would deploy those into the Pacific to track Soviet launches. And the Chinese, of course, have equivalent vessels for tracking and tracking the telemetry of missiles. These are targets in China. Most of these are airfields, the kind of targets that are important because aircraft can carry nuclear weapons. This is a comparative study of 8 space programs, which is important because space programs use many of the same technologies as the nuclear arsenals of states that are launched by missiles. Now, most space programs use liquid fuels, which in some sense are sometimes, depending on the fuel, they're more environmentally friendly. At other times, they can be toxic and corrosive, and they take a time to fill up the rocket. So during the early Cold War, the Soviet Union had liquid-fueled rockets, and it would take them 45 minutes to fuel up the rockets, and this was visible if the rockets were not in a silo. Whereas with a solid fuel rocket, which the Soviets didn't adopt until the late 70s, early 80s, you press a button, there's ignition. And so the solid fuel rockets are very much like the children's toy rocket engines that you can buy in a hobby shop. So here you can see the number of launches and the experience that countries have doing those launches. And so you have a lot of countries that do launches that are not necessarily countries that possess nuclear weapons. So you've got Brazil, Israel, Japan making a lot of launches. It indicates their first launch in low Earth orbit and geosynchronous orbit. Low Earth orbit is basically very low to Earth, and the geosynchronous is high enough that it follows the geography of the Earth. It shows the first use of cryogenic technology and the amount of money that's spent on it. And where the launches occur matters. Japan recently changed their launch pad from an area that's quite close to China to an area that's farther from China. So clearly there's a merging of these two sites. We had a guest speaker once in this course, which is really fantastic, who's now Minister Mark Garneau, Canada's astronaut, also former head of the Space Agency, and also from the Navy. And we asked him what kind of payloads did he have when he was going up and down in the space shuttle, and he told us, without revealing too much, that half of the payloads in NASA's space shuttle were military, or the National Reconnaissance Office that operates all of the spy satellites. So space programs are, at least in the American case, 50% military application, and during war the space shuttle probably would have been used to scoop up and damage Soviet satellites in orbit, a very dangerous mission. So it's definitely a paramilitary type of organization. So this is a MIRV, multiple independently targeted reentry vehicles, and you can see here On the left, a tracer showing how these were coming into the atmosphere. These could be, in fact, much more widely dispersed than is the representation here. And different sized missiles have different sized buses that drop these individual warheads. Now, you do have some of these buses guided by Navstar satellites, so they use either optical tracking of the stars to know where they are, or they get signals from deep space GPS systems, so they know how to guide themselves to their target. And as we spoke about earlier, it's a lot more efficient to have lots of small warheads than to have one big warhead. And so all of this is about increasing efficiency and effectively spreading, and as even as possible, the minimum amount of pounds per square inch overpressure necessary to destroy a city or a fixed hardened target like a bunker or a silo. Here you can see work on the warheads on a bus. Now, the math of MIRVs is to maximize reliability. Whenever you have a target, you would have warheads coming in from different missiles at almost the same time. You wouldn't want it at the same time, because then you'd have this fratricide effect with one warhead destroying the other. Nuclear warheads are very delicate. If you drop them, you break them. They're not like conventional explosives. So the math is to have this redundancy where you have targets with duplicate strikes, but coming from different platforms in the event that the platform is intercepted or malfunctions in flight. You can also see here the jagged maneuvering of the bus as it's releasing the different warheads, and this then releases them on their different ballistic trajectory. Here you can see the Minuteman III re-entry vehicles streak through the sky near Kwajalein Atoll in the Ronald Reagan Ballistic Missile Defense Test Site. And again, this is a very narrow distribution of those warheads from the bus. It could be much more widely dispersed. So this is a much broader view of the different types of exchanges. I'm going to pull out my pointer here so you can describe it. So we have here a satellite which detects the Soviet launch. Here you have the bus. It releases the warheads ballistically. Here's a sensor which picks up that launch. Here you have a Soviet submarine which probably would have launched this rocket first. This rocket would go up here and detonate here. Now the purpose of the detonation is to send out an electromagnetic pulse which would then inhibit the radars of any interception capability. So the rockets would then come in, and the U.S. would be blind as to what their targets were, whether it would be cities or military facilities or silos. And then, of course, the U.S. would send out their retaliation as quickly as they could. That would be launch under attack, or LUA, which is the practice of launching missiles while you are being the target. So this is from an Office of Technology Assessment study done about what a nuclear attack would look like against a given discrete target. And what we have here is a Minuteman III dropping warheads, at least two Minuteman III rockets dropping warheads in a pattern on what was then Leningrad and what is today St. Petersburg. And you can see you have the 12 psi core detonation and then the 5 psi outer ring and 2 psi. And the goal was to basically knock over the buildings. And that's what that detonation would have done. Now, ICBMs were based in the 1950s in garages on the surfaces next to airfields, which made them very vulnerable. Since then, they've been based in silos. Now, silos are rated by the PSI resistance of the cement, and it is really quite incredible. I'm an Army engineer, again. I was an Army engineer officer, and in British Columbia, our Canadian Forces base Chilliwack, which is where the engineers were based in those days. I think today they're based in Gagetown. They had a center for research and development where people worked on cement. It was unbelievable, and they worked on the most incredibly strong cement. Obviously, their focus was on bunkers for communications and airfield surfaces. So if we were to get into a war and the airfield was damaged, you could very quickly patch it up. It would dry, and then you could have aircraft use it. So here we have a missile deployed inside a silo, and the upper end of some of the silos is about 6,000 psi, which is enormously strong. amount of resistance. So you'd have to get a nuclear warhead to be right up next to the silo in order to cause that level of damage. Now the missile that you see depicted here is a French SSBS Warhead 2 in its silo. The French had silos on the Plain d'Albion in southern France, and they had these aimed at the Soviet Union during the Cold War, but they've since been dismantled and removed. I mean, one of the key things here, you can see in the picture here, is the top of the silo that have to come out to then permit the rocket to launch. And that lid would be there to absorb incoming strikes of weapons. Although, in theory, you'd want to launch the missile before the strikes arrived at your silo. And even though the soldiers trained very quickly for that drill, I doubt very much it was feasible, because I'm not sure if the politicians, particularly the U.S. president or the Soviet leader, could have acted fast enough to make a decision to launch before the enemy's missiles impacted on the silos. Doesn't mean that the missile in the silo would have been destroyed. It all depended on the probabilistic accuracy of the incoming missiles. So here's another depiction. This is an American site showing the deployment of their missile. This one looks like Peacekeeper. Now this is actually a standard setup for the silo, particularly the command module that you can see here on the left. And you'll see other pictures of these. So this is clearly an American silo set up in an area where there's mesas. So probably somewhere in the southeast of the US. Now this is a basing concept used for the MX, or the Peacekeeper missile, that was never implemented. And the idea was you would have these MX missiles very close together. And you'd think, well, this is absurd. Well, it's not absurd, because for a Soviet warhead to destroy one of these silos, it'd have to be right up next to it. And for that to happen, you probably would destroy 2 or 3 missiles with one detonation. But on the other hand, the Soviets could only do one detonation per sequence, maybe one missile coming down every 30 seconds or every minute or every 3 minutes. And so the Soviet missiles, by detonating and blowing each other up, and that's called fratricide, where you kill a brother, would mean that the Soviet missiles themselves would provide missile defense to the site. And so the Americans could then launch at a moment when they thought there was a delay or a pause in the firing, or in the pauses between the arrivals of different Soviet warheads, and then launch these rockets. This was never implemented. This is another concept of having the Peacekeeper missile in a train move underground in a tunnel. But the train, in certain parts of the tunnel, which were not armored, you can see in the bottom left you had an encased cement portion of the tunnel, but the rest of the tunnel would have loose earth above it, and it wouldn't be very deep, and these trains could then push out through the sand and then launch the rocket from underground. Again, this was never implemented. The main reason is that the US, their level of accuracy increased enormously, and they anticipated the Soviet accuracy of missiles would increase, and so missiles in silos are incredibly vulnerable today. The reason the U.S. keeps missiles in silos is they're highly visible symbols of general deterrence, which, as you know, is important. General deterrence is when you have enough power that you're able to deter the enemy from even considering a competition against you. And so it's a visible representation of U.S. power. Real U.S. nuclear deterrence is in their submarines. They're underwater, they're very silent, and they're very far, and their missiles have very long range. And so for the Chinese to stop an American submarine, they'd probably have to chase the submarine to the South Atlantic or the Indian Ocean. These are not next to China. They have incredible range. So visible silo-based missiles send a message, even if they are vulnerable today because of some countries having high accuracy. So one solution the Soviets had and the Russians today is to take the rockets out of the silo and put them on vehicles and roll them around the countryside. And so the Soviet Union developed the SS-25 road system. Now these originally had to be launched at pre-designated points or anywhere along a path of deployment, but they probably have the command and control and geodetic skill to be able to launch it anywhere. So you can see first on the top left the SS-23 road mobile system. You can see a Cold War Scud on the bottom left. Those were more theater weapons, not intercontinental systems, but they were mobile. And in this case, they're tracked, so they could go inside a forest or in rugged terrain. But there's also road mobile versions. And you can see on the right the People's Liberation Army DF-21 road mobile system. The Soviets also developed the SS-24 rail system. Now the SS-25 road system was ended in 2016, and it's possibly been revived, and the same thing happened with the rail system. It was canceled and then sort of reinitiated. You can see on the left the system with the rocket raised. So there are tracks in eastern part of Russia, in Siberia, rather the eastern part of sort of Eurasia, Russian Eurasia, which give sufficient space to be able to move these trains around without having them disrupt the normal rail traffic. In times of peace, both the road and the rail mobile systems stayed in a compound, and they were only deployed out and dispersed when there was anticipation of a crisis, which, to my knowledge, never occurred. So I don't think there was ever a crisis-related deployment of the system. The SS-25 also had a mobile command center. I'm not sure if it was attached with or independent of the train carrying the missile itself. This is the Russian railroad network today, showing some of the cities, so you can see how you can situate it. And so those trains would move along those rail systems. So we're really looking at central Russia, around the space of the Urals, because out in the east you have a pretty linear rail system, so it would make it pretty easy to isolate a nuclear rocket. And plus these are ICBMs. They don't really have to be close to a target in order to launch. Here you have a color-coded distribution of the main deployment areas. Where it's green is exclusively rail, and where it's red and green, it's both road and rail. Roads are obviously an issue when you're looking at the permafrost of Siberia, so you have seasonal access to some of this terrain. The trucks carrying the SS-24 road mobile system are wheeled. They need a road. They're not going to be doing well in a marsh, even if it's frozen. You're going to be confronted later in the course with some very stark choices that are not going to be entirely theoretical, because you're going to be playing simulation after simulation where you'll be asked the same question over and over again, and you're going to explore through choice what you should do, and then we're going to see the consequences. And this is a technical first component that you need to be very familiar with in order to make that judgment. And this is a process we're going to build up over many lectures, and it's offering two philosophies on how to fight nuclear war that are diametrically opposed. So let's start with this. The concentration of force. So the key to winning in battle, and this has been a truism for thousands of years. The concentration of force has been mentioned by Sun Tzu, by Yamini, Napoleon, Clausewitz, and endless other strategic writers from different cultures on different continents in different millennia. It's a very profound observation, and we've mathematized it in the 20th century. The key to winning in battle is achieving a concentration of force against your opponent's weakness and denying them the same. The opponent's weakness is normally referred to as the center of gravity. This, the most important principle of combat, that is the core of the military profession, is the principle of the concentration of force. And it is that at the point of attack, you always want to maximize the concentration of your force against the weakness of the enemy. The greater the difference in strength, the greater exponentially is the difference between the losses of the stronger and the weaker side. Okay, and we can be very precise about the mathematics. It's actually the inverse hyperbolic 10. In the picture, you see a very large hallway with missile silos. This is actually the interior of a U.S. Ohio-class ballistic missile submarine. Now, we use the Lanchester square law to model the concentration of force. Lanchester was a mathematician who helped develop these equations. Now, the mathematical relationship in warfare is unique and is captured by these equations, particularly the square law version of these equations. And they're written about a century ago, shortly after Lanchester's equation, as a stretcher bearer in an ambulance in the trenches of the First World War. And it essentially explains how firepower creates victory. The essential verbal description is that the greater the firepower superiority of Army A over Army B, the greater the exponential, or specifically the inverse hyperbolic tan, difference in their battle losses. Now, the basic logic of the Lanchester equation is that there is an exponential increase in the ratio of the firepower, as there is an arithmetic increase in the ratio of the units that are firing at each other. And its peculiar consequence is a wildly disproportionate infliction of losses that creates different loss curves until one or the other side is terminated. And this applies to nuclear weapons because nuclear weapons are basically bullets being fired at targets. And so I'm going to show you now the precise logic and the precise math behind it. And once you've looked at that, I'm then going to show you the impact of the application of that logic. The second most important principle of war is the concentration of force, also called mass. This has been identified by authors as diverse as Sun Tzu, Karl von Clausewitz, Jomini, Napoleon, U.S. Operations Manual FM 500, the Prussian Military Command. It has a special characteristic. Here you can see a display of 4 soldiers encountering 2 soldiers on the other side. And we think about the power ratio. Well, we have 4 soldiers and they're confronting 2 soldiers. So we could divide 4 by 2 and we could see that there's a power ratio here of 2 to 1. So if there was to be an exchange, maybe 2 of the 4 soldiers that are here would die and they would exchange their lives for the 2 soldiers that are opposing them. But let's take a deeper look at what the actual ratio is. In a given unit of time, each soldier will be able to fire 1 bullet. Now the 4 soldiers on the left will be able to concentrate their fire. So these 2 soldiers will concentrate their fire here, and these 2 soldiers will concentrate their fire here. The soldiers that are responding, the smaller group of 2 soldiers will respond, but they'll have to divide their bullets in half because they have 2 targets, not 1. So they're going to be firing back half a bullet each against each of the targets. Half. Now what governs the ratio is not the total number of soldiers, it's the ratio of the firepower between each of the soldiers. Each of the soldiers on the left is receiving half a bullet. Each of the soldiers on the right are receiving 2 bullets. That is the real ratio. What is the ratio of half to 2? That's the ratio of 1 to 4. That means when you have a numerical advantage that's twice, your firepower advantage is actually 4 times. This is the first property of the concentration of force. It has huge political consequences. Military leaders are trained very early on to show up as quickly as possible with as much as possible, so at the point of contact they are not outnumbered. It doesn't mean soldiers like war. It means soldiers dislike defeat. Let's take this to a more extreme level. This is the second characteristic of the concentration of force. We're going to reduce the group of 2 soldiers on the right to 1 soldier. They encounter each other inside a forest. Here you have a nominal numerical ratio of 4:1. 4 soldiers to 1 soldier. But again, let's count the exchange in terms of firepower. We have 4 soldiers firing on 1 soldier. So 4 bullets are coming in. This soldier is firing a quarter bullet at each target. A quarter to 4 is a ratio of 16 to 1. So this is the second property of the concentration of force. As the ratio increases arithmetically, the ratio of firepower increases geometrically. So there is severe punishment, a disproportionate set of losses suffered by the weaker party. The equations that model this relationship are called the Lanchester equation, and they reveal specifically that there is an inverse hyperbolic tan increase in losses as the ratio of forces increases. Now, the Lanchester equations are used to model a particular phenomenon that's been observed in warfare, and that is that you don't have a proportionate set of losses between sides. You actually have losses that are cumulatively disproportional, and the actual loss rate is the inverse hyperbolic tan. And this is crucial because it's actually counterintuitive, and it has a whole bunch of both military and political consequences. So it's important to know how the Lanchester equations function. So the way that we're going to approach it is we're going to look at it in 3 different steps. Okay, and these are consistent with the assignments you're going to have to do. So the Lanchester equations have a first part, and the first part is intended to determine which is the stronger side. This is important because in the equations you have 2 sides. You've got red and blue, and red designates the stronger side at all time. So the first goal is to identify which side is the stronger. So to determine the greater force, we have this formula here. It's going to be small r times big R at time 0. So 0 doesn't mean 0 quantity. It means at the beginning, at time 0. So you take the initial force, and you then compare that to small b times big B squared, also at time 0. Now, it doesn't matter at this stage which force is given which color. The important element here is that once you've done the calculation, the larger force, the larger net force, is given the identity of red in the second and the third equation. So here we've got 0.01 for both small r and small b. These are efficiency coefficients. And then we multiply by the number of combat units. In this case, for the arbitrary red, we've got 200. For the arbitrary B or blue, we've got 150. So it's 0.01 times 200 squared versus 0.01 times 150 squared. And when you calculate it out, we end up with 400 versus 225. And 400 is the larger value. So these values that are red will continue to be red in the remaining 2 equations. Now the second equation answers the question, how many soldiers, when they're fighting, how many turns will the battle take? Okay, so it's battle end. When will the battle end? This is the most complicated of the equations and the ones that students have the most difficulty with. Essentially, it's about how to apply the inverse hyperbolic tan, and we'll talk a little bit about that. Okay, but let's look at the formula first, or the equation. It's going to be small r times small b, and remember now, r here is the identity of the larger, stronger force. Not necessarily the larger force, but the stronger force. So here we have the 2 efficiency coefficients. They're multiplied against each other. You take the square root, and then you get the reciprocal. Basically, you put a 1 on top. Times the inverse hyperbolic tan of, and here we see BO and RO again. And these are values at the initial strengths when the battle begins. So we take B's initial strength, and which we know to be 150, and R's initial strength of 200, and then we multiply it by the square root of the B's coefficient of efficiency by R's coefficient of efficiency. So now we can insert the values. Small r and small b in this case are both 0.01. We put them in here, multiply them against each other. We take the square root, and then we have the reciprocal, basically all under a numerator of 1. Now if we calculate that out, it's basic arithmetic. You can use a calculator on your cell phone or your computer. You end up with 100. Now here we've got the predicate of the trigonometric function. So we've got b at time 0 over r times 0 times b over r. So it's 150 over 200 times the square root of 0.1 over 0.1. That's obviously 1. The square root of 1 is 1. So this whole element here turns into 1 and disappears. And we have 150 divided by 200, which is 0.75. So here we arrive at the problem. 0.75 is the predicate of the inverse hyperbolic tan, which means we apply the inverse hyperbolic tan to 0.75. Do not try to apply it to the number in front of it, which is the 100. Whatever this calculation is, we then multiply the value by 100. So the inverse hyperbolic tan of 0.75 is going to be 0.9729. And then we multiply that by 100, and that gives us 97.29. So this engagement is going to go through 97 turns, at the end of which the weaker party, in this case blue, will be completely annihilated, and some unknown number of red will still be around. So that's what the second equation here does. So let's go on now to the third equation. The third equation answers the final crucial question: how much of red force will survive on the last turn of this engagement when blue is completely annihilated? So what is the strength of the victor at the end? R end. So the formula here is R at time 0 times the square root of 1 minus, and the numerator is the B's efficiency coefficient, times B squared at time 0, so the total number of forces times itself, divided by small r, the small r coefficient of efficiency, times the big R squared of units at time 0. And if we plug in the values, it's going to be 200, which is the number of forces of red, square root 1 minus 0.01 times 150 squared, divided by 0.01 times 200 squared. That's going to give us 225 over 400, 1 minus that value. And you can sort of relatively simply calculate this out. There's a couple of more steps. And we end up with a value of the forces of red at the end of 97 turns of engagement will be 132.28 soldiers. And the number of blue soldiers at the end will be 0 at the conclusion of the battle at the end of turn 97. So here is the math that I used just previously, in case you want to see it in a clearer format. There we have China's Lop Nor nuclear detonation in Xinjiang province, which is their region, which is populated by the Uyghurs. And this was China's first nuclear test. Here you can see more of the equations. And you can see a missile launch. Here is the third and final Lanchester equation, and here you see a Tupolev 95 bomber. I visited NORAD headquarters in Cheyenne Mountain, which is very interesting because it's a joint command for North American defense, operated both by Canadians and Americans. And so it's familiar there. Nice to see familiar faces, familiar uniforms, the Canadian soldier. Now, during 9/11, the deputy commander who was in charge at the site, because the commander was elsewhere, was General Penny, a Canadian general. And when he heard of the strikes on the buildings, he immediately closed the door on the site, and he put out the requirement that all civil aircraft land. And that's the reason why the civilian aircraft landed. He wanted to get control of the aircraft. But the original design of that command, which is sent out from NORAD, as well as another site at DEFSMAC, is that in order to clear the airspace to facilitate the launching of nuclear bombers, nuclear tankers that give them range, and nuclear missiles, and to detect incoming missiles, all civilian aircraft had to land. And so we had a Canadian in charge. Now, when I went to see him at NORAD, I asked him, do we still have Russian aircraft flying? And he said yes. He said, in fact, it's routine for the Russians to fly Tupolev 95 strategic bombers. And this is the Tupolev 95. Not very fast, those are turboprops, but it has incredible range. And even though it's a very old aircraft from the 1950s, because of its range, it's still being used. It could virtually fly around the world. And so it can carry powerful sensors instead of bombs, which is what these versions do when they fly off the Canadian coast, even today. So now let's apply these in 4 simulations. We're going to run 4 models. I'm going to show you the inputs and the outputs. In the first, we're going to run 2 sides that are approximately equal. One outnumbers the other side. Then we're going to look at 2 forces that have a very small initial difference. Then we're going to look at a side in which one side is very significantly advantaged over the other. And then we're going to look at another side where a weaker party has a higher effectiveness rate and is attacking a stronger party with a lower effectiveness rate. Here you can see a sea-launched cruise missile, which is bursting out of the water after having been launched by a submarine. Any submarine can launch these, virtually any, and they're launched from the torpedo tube, so you don't need vertical silos. So here's our first simulation. We imagine 200 Reds. It could be ships, soldiers, rockets, artillery, airplanes, tanks, and they're fighting 150 Blues. Now in this particular simulation, their effectiveness is held constant. It's the same between each other. It's 0.01. So let's run the simulation. Red starts at 200, Blue starts at 150, and notice that as Blue suffers more and more, the curve that Red is suffering slows down. So Blue ultimately goes to annihilation. They're wiped out. Red still has 132 soldiers. So you see that a 25% difference allows 2/3 of Red to survive. That is very disproportionate. So this captures the consequence of the Lanchester Square Law. It's fairly profound. It tells us a small difference like 25% is going to create a huge, enormous outcome. In the second simulation, we're going to run a much tighter difference between the 2 parties. And this, I think, really captures most vividly the impact of the Lanchester equation on a combat interaction. Again, we've kept effectiveness constant between both parties. We have 200 Reds against 190 Blues, and in terms of performance, the individual units are equally efficient. See, a tiny difference at the initial point, and over time, Blue goes to annihilation, but Red still has about 1/3 of their units survive. 62 units survive. So the tiniest differences can create enormous consequential outcomes at the end. In our third simulation, just so we can see what it would look like, we're going to run 200 against Red against 100 Blue. Again, the effectiveness is constant. And here we can see 173 of the 200 Reds survive, and Blue again is annihilated almost in a straight line. So showing up with half as many of anything on a battlefield without having some other advantage like maneuver or training of the soldiers or firepower or geography will lead to this terrible outcome. This is why soldiers hate to show up late with not enough stuff, and why initiative matters, because they want to be able to maneuver and hit the opponent's weakness before the opponent hits their own weakness. So let's run the fourth simulation. Here we're going to have a weaker party, Red, attack a stronger party, Blue. And when I mean stronger and weaker, I don't mean in the Lanchester sense. I mean it in the sense of the number of units that are attacking. But Red will have twice the effectiveness, 0.04. So here we see Red still prevailing, Blue being brought to annihilation, and you've got about 7,900 of Red that survive. So all of these indicate, using different values, the significant impact of the Lanchester equations. So what are some of the observations? Well, we have decelerating loss rates for both sides. Now this is if you had robots fighting each other, or rockets. But in reality, humans, when they fight, they have breakpoints. They have a sense that defeat is coming, and then some of them run away. Now in the 18th and 19th centuries, it was observed that the highest losses occurred when one side ran away. It sounds very peculiar, but in early battles involving melee weapons like swords and spears, it was more like a brawl. It was like a rugby game. People pushing back and forth. People got injured, but they got injured a lot. And you can get stabbed quite a few times before you actually die, or slashed, or hit with a mace or a hammer or an axe. But when people get scared and they turn around and they run away, they expose their back. They're no longer working in a unit with other people, but they're isolated. And they're running in a direction they're not sure where. They're very often lost because there's no one telling them what to do. And most of the losses, we're talking over half of all the losses in many of the great battles over the last thousands of years, including the era of firearms in the 18th and 19th centuries, were lost when people were running away. So breakpoints are important for other reasons. If you can push someone to a breakpoint because they're losing the Lanchester fight and they run away, that's when you get all the losses. The second observation is that there's a disproportionate increase in the difference of losses between the two sides based on the difference in their initial military strength. So the initial military strength matters a lot. The Lanchester equation is the core of every operations research model that examines combat. Now in the pictures we can see a frog, a free rocket over ground, which is a trucked Soviet missile, which was the initial version of it was called a lunar rocket. And the other system we can see is a nuclear warhead being carried inside what I believe is F-111. Why are we going to Greece? Because the Lanchester equation was identified thousands of years ago. There was a revolt by the Thebans against Sparta. Thebes, you can see in the center map. It's slightly northwest of Athens in Boeotia, and it was basically a city surrounded by farms. They had a smaller population than Sparta. They had almost no military tradition to speak of, so their farmers were much less well trained. They had fewer weapons than the Spartans, but they had a leader, Epaminondas, who understood intuitively the Lanchester equations. So General Epaminondas confronted the Spartans at the Battle of Leuctra in 371 BC, before the Common Era. He was outnumbered and he was qualitatively inferior, but he knew about a practice of the Oblique Order, which was done quite often. The Greeks fought in phalanxes, which were large concentrations of soldiers with spears that were very long. Again, like a rugby game. Big, thick, packed masses of soldiers who would then push against each other. And what he did was, if you look at this display, on the top of the map you've got your Spartans and your Spartan allies, Phocians, Philasians, Corinthians. At the bottom of the map you've got the Thebans, along with some of their rural allies, like the Boeotians. So Epaminondas took the Boeotians and had them lay at an angle, and he had the ranks very thin. And the land was sort of undulated. And he told the Boeotians, I want you to march, but I want you to march at an angle slow enough that you never get to the Spartans. Sort of a Zenos arrow paradox, right? Where before you can get someplace, you got to go halfway, and before you can get halfway to there, you got to get halfway to there, and it goes on infinitely. And although that particular paradox has been solved, it wasn't solved for the Boeotians because they actually never did successfully make contact in combat. They basically just sort of floated in front of the Spartan army and their allies to keep them occupied. And because it was relatively flat terrain, the Spartans didn't think the formations were so shallow, they thought they were much thicker. So what Epaminondas did was he took the rest of his army and stuck it in a giant block on the left, which you can see. And he marched that giant block forward. And when that block impacted, it hit the Spartans head on. Now, the Spartans were more skilled. They had a higher effectiveness. But at the point of contact, the Thebans and their allies had sufficient superiority quantitatively that it compensated for their lack of quality. So Epaminondas leveraged the insight of the Lanchester equations to create a concentration of force at the decisive point. And the impact was the Thebans won locally. And once they won locally, they were able to burst through the Spartans, and guess what? All the Spartan allies deserted and ran away. This was the battle where the Spartans, probably the best individual warriors that history has ever seen, were defeated on the battlefield by farmers led by a man who knew math. The results were the Spartan leader, Cleombrotus, was killed. The Spartans retreated. They lost 2,000 men. Their hegemony ended forever. The Oblique Order, as a technique to achieve a localized concentration of force, was identified consciously and used by Alexander the Great repeatedly. The Battle of Granicus, the Battle of Issus, and the Battle of the Plains of Arbela, or the Great Battle of Gaugamela, that ultimately destroyed the Persian Empire. Frederick II of Prussia used it, and many others. A second very important concept that needs to be understood if you're to understand warfare, particularly nuclear warfare, is the mixed game strategy, which is the logic of probabilistic warfare. This is important for two reasons. One, it has a core powerful effect in the same way that the Lanchester equation does. And number two, more importantly, it is completely counterintuitive and opposite to what a normal, commonsensical individual would choose to do. Now, in warfare, like in, say, boxing, it's a competition. And things are not always equal. If you were to face off against, say, a boxer, and let's say their left arm was much stronger than their right arm, right? And you wanted to defeat them. Well, obviously, you would compensate by trying to protect yourself more from their stronger left arm than their weaker right arm. And the logic of that is to make them indifferent between the two choices. And you want to make them indifferent between the two choices because then they can't exploit you. Now, that sounds like sort of a fairly simple proposition, but it's actually possible to mathematize it in such a fashion that we can get precise instructions on how frequently we're supposed to play what we do to counteract what they're doing. Now, the equivalent in warfare on land would be, say, you're going to be attacked on your broad front, and you're protected on one side by mountains, on the other side by a forest, and so you would privilege putting more soldiers in the forest than you would in the mountains, because your defense is basically the very strong defense of the mountains plus some soldiers versus the very strong defense of a lot of soldiers plus a few trees, and it would balance out, and so the enemy would have no advantage advancing on you. And so we want to be able to mathematically precisely apply that. Now, John Nash of movie fame was a game theorist, and he actually came up with a mathematical theorem which showed that the mixed game strategy is the most efficient way of specifying how to make your opponent indifferent between their different choices. Now, there's always a better solution. The best solution is to have a spy in the enemy camp and to know where and when they're going to launch their missiles. There was an espionage case in the 1980s, which is probably the most damaging espionage infiltration of the U.S. ever. There was a family called the Walker family. A whole family were involved as spies for the Soviet Union, and they gave the Soviet Union the codes for some of the launches for the U.S. nuclear missiles. It was the most damaging espionage case in U.S. history, besides the Rosenbergs, who funneled Manhattan Project nuclear weapons development secrets to the Soviet Union. So we don't have a spy necessarily, and if you don't have a spy, then John Nash's solution shows that this is the next best thing. So military outcomes are the result of strategic interaction because you've got two players that interact, and so we're going to look now at games theory to see what the different steps are we have to go to ultimately come to our mixed game strategy solution. So you might recall the prisoner's dilemma. The story is, of course, the narrative that two individuals go to rob a bank. They're arrested in the lobby before they even begin to rob a bank, but they're charged with robbing the bank. The police then isolate them, And the police incentive, of course, is to have them go to jail. And if they only get one of them to go to jail, they need to make an example, so they put them in jail for an extra long time. If they don't manage to get them to admit or to finger each other, then they can at least charge them with trespassing for 3 months. If both of them are discovered to be thieves, then they would both get 5 years. Now, the prisoners can't communicate, they can't coordinate, they have to sort of anticipate what the other would do. And so the question we have for a prisoner's dilemma game like this is, what is the outcome going to be? Okay, so here we have two players, player A and player B. We've got two columns of choices called strategies for player B, cooperation and defection. For player A, we have two rows of strategies or choices called cooperation and defection. The diagonal lines that are there to remind you that the lower left payoff or utility is for player A, and the upper left utility or payoff is for player B. Now here, we're talking about prison time, so the lower the number, the better. So 0 is better than 3 months, 3 months is better than 5 years, and 5 years is better than 6 years. So how do we play the game? So player A has a choice between cooperation or defection, the red row and the green row. And the way that we solve it is called seeking dominated or dominant strategies. Okay, we want to find out if one strategy is superior to the other. So let's compare. The way we do it is we compare the values in the different cells. So for player A, we look at the column for player B, the first column, and that would be on the left. And we compare 3 months in cooperation with 0 time in jail in defection, the green versus the red. And clearly player A would prefer to have no time in jail at all. Then we go to the next column of player B, and we compare the two values for player A's choices, 6 years, which is in green, for cooperating, or 5 years for defection. And obviously 5 years is better than 6 years. So player A will always choose red. There's no reason to choose green. Now player B again has the same two choices, red versus green. It's a symmetrical values, and we can again do the same comparison. 0 time in jail is better than 3 months in jail, and 5 years in jail is better than 6 years in jail. And so player B will always choose defection. So by eliminating dominated strategies, we can then know what strategy they would never play. So this then leads us to the Nash equilibrium. Now the definition of a Nash equilibrium is, once you've eliminated the dominated strategies and you have a dominant strategy, then the dominant strategy reveals to you when they intersect what the Nash equilibrium is. And a further check on the Nash equilibrium is, once you have that Nash equilibrium, neither player will have any incentive to change. All right, they're not going to change their strategy. If you were to say, hey, do you want to change now again? Do you want to change a different strategy now that you've seen the outcome? If they say no, then that is definitely the Nash equilibrium. If they say yes and they want to stay, that's the Nash equilibrium. But if they want to change, then we have a problem called cycling, which is described by the Condorcet paradox, which is not the subject of this course. So here we have player A choosing defection. Here we have player B choosing defection. So here we have the intersection of the strategies chosen by player A or player B, the two dominant strategies. They overlap, in which both players go to jail for 5 years. This is the Nash equilibrium. And we can confirm it's the Nash equilibrium because we can offer player A or player B a choice of a different choice. So player A, would you like to go from defection to cooperation? Well, let's see the playoff change. If player A goes from defection to cooperation, which is the row of defection to the row of cooperation, they'd go from 5 years to 6 years. And player B, same thing. If you could offer them a change of their strategy from the column of defection to the cooperation column, they would go from 5 years to 6 years. So there's no incentive for them to change. Therefore, this is confirmed as a Nash equilibrium. Now, it's a suboptimal outcome. It would have been far more intelligent for player A and player B to cooperate and each get 3 months. But the lack of ability to coordinate led them to this result. Two players fighting each other are not cooperating, but they do have an incentive to exploit each other. And you can design a game that shows that attempt to exploit, which is what happens in warfare. So here we have a hypothetical game, and I've made it a bit more complicated because we want on this table to do two applications. We want first to apply the technique of dominant strategies to eliminate strategies that would never be selected, and then we want to further apply a mixed game strategy. So let us proceed. So let's make this player A and let's make this player B. It's actually arbitrary at this point. Doesn't really matter. We have rows and columns. So let's compare the values. between forward and right, which strategy would be preferred? Well, we see that 2 and 2 are the same. They're equivalent. 1 and 1 are the same. 3 and 3 are the same. But you know what? 2 is better than 0. So player B is never going to choose this row. And by eliminating the row as his choice, the numbers there also are irrelevant for player A. Player A is never going to encounter those outcomes because this choice will never be made by player B. Now, doing this search for dominant strategies does involve a certain trial and error. Right? So you have to go back and forth to solve it. Although this particular table is much simplified. So let's compare left and withdraw. Well, 2 is better than 0. 2 is better than 0. 0 and 0 are the same. And 3 is better than 0. So, you know what? B is never going to choose withdraw either. Just not possible. The payoffs there are not very good. Here, of course, it's the opposite of the prisoner's dilemma. The player utility is for the highest possible value. So let's take a look at player A now. Player A has a choice between 2 versus 1, so 2 is better than 1, and 1 versus 1, which is the same. So player A is never going to choose to go forward. Let's compare now 1 versus 0. Well, 1 is better than 0, and 3 is better than 0. So player A is never going to choose to withdraw. The net effect of this is to leave us with just the 2 central cells, or these rather the 2 rows and the 2 columns. That leaves us the 4 central cells. So let's see if we can't come up with something here. Do we have a dominant strategy? Let's start with A. Well, 2 is better than 1, but 3 is better than 1. Oh, that's a problem. This is called cycling. It means that there is no dominant strategy. All right, so let's take a look at B. Maybe there's a solution here. Maybe we can unlock with B. So for B, 2 is better than 1, but 2 is also better than 0. So we have cycling among both actors, which means we cannot use a dominated strategy to solve. So what we're left here with are the core choices from that strategic game. Now you'll notice the feature with this central square is that we have no dominant or dominated strategies. So for example, if we were to look at player B and we were to compare their choices, we notice that 2 is greater than 1, but 3 is greater than 1. So the 2 strategies, they don't dominate each other. As well, for player A, we see that 1 is less than 2, but that 2 is greater than 0. So their 2 strategies of left and right also don't dominate each other. So we're at sort of a logical impasse. But we have a mathematical solution. It's called the mixed game strategy solution, and it involves a little bit of algebra. The way we should conceive of this is like a boxing match. You have 2 people fighting each other, but their arms are not symmetrically equal. They're not equally strong. If someone were to attack you and they had a stronger right fist and a weaker left fist, right? You would end up in a game of, I want to think what they're thinking about what I'm thinking about what they're thinking. Because if you always defend against the strong right punch, their left punch is going to hit you. And even though it's weaker, it's going to get through more often because you're not defending against it. So mathematically and conceptually, what you want to do is you want to divide your defense so it's proportional to their stronger right arm and their likely more frequent weaker left arm, right? And so psychologically what you're doing is you're making the opponent indifferent between their choices. It doesn't matter that their right arm is stronger because you're going to maneuver in a way that causes them to swing with the right arm less. Because you're going to defend disproportionately against the right, but not so much so that it gives the left an advantage. So that's the type of solution we're going to create using algebra. Now another way of thinking about it is militarily. Here we have a depiction of a battlefront. And you can see on the left side there's a little forest. In the center is an easy road leading on to the horizon. And on the right we have these difficult mountains. Now defensively, if you're trying to protect against an advance, the mountains are the easiest. You wouldn't need a lot of soldiers in the mountains. The road, you need to barricade it. You need to put a lot of soldiers there because it's such an easy route. And the forest, it's not as easy as the road, but it's a lot easier than the mountains. So you could put all your soldiers on the road, but then it would leave the mountains exposed, and then the enemy would sneak through the mountains and attack you from the rear. So the idea is not just to defend one of these. The idea is to defend all three, but in proportion to how easy they are to exploit. So you'd put the most soldiers on the road. You'd put a medium amount of soldiers in the forest, and you put a very small number of soldiers in the mountains. So that the geography plus the soldiers in the defense will make the opponent indifferent. It doesn't matter whether they go through the forest, the road, or the mountain. It'll be equally difficult. Because the difficult terrain will be counterbalanced by a small number of soldiers, and easy terrain will have a lot of soldiers defending it. So that's what we're going to do here. Now, a note on the terminology. Traditionally in mixed game strategy, the variables that are used are theta 2-1 and theta 2-2 for actor B, and theta 1-1 and theta 1-2 for actor A. I like to do it this way because I think it gets you into the mindset of the terminology used by the creators. And one of the creators of this, of course, is John Nash. But you could easily replace these with X and Y and A and B, and it'll be a lot easier. Theta 2-1 or theta 2-2 are not numbers. They're just a name. The numbers here are just a name. So it's a variable identifier. That's all it is. So we have here these values. We know that we have no dominant or dominated strategies, so there's no canceling out of strategies, so we have to solve this. Now this is one of the surprising theorems that comes out of mixed game strategy. These values are diametrically opposed to each other in the sense that there's a zero-sum game. Any victory for B is a loss for A, and we have to have that assumption for this to work. So these are two adversaries that have no incentive to cooperate. They're at war with each other, or they're in conflictual relations. So the logic in analyzing this requires you to make the opponent indifferent. Okay? That's not the best outcome. You know what the best outcome would be? If you had a machine that could read the mind of your opponent. If you had a spy in the enemy camp who could secretly tell you what they're planning to do, that would be the best possible outcome. But we don't have that. And so the next best thing is to structure our behavior and make the opponent indifferent. And there's a theorem that proves deductively that that is the best solution. Right? Now, this is the peculiar thing. It doesn't matter what your values are. It matters only what the opponent's values are. So we're going to use the opponent's values against them. We're going to take the distribution of gains for the opponent and use it to structure our behavior. We're not going to use our own values. It's completely counterintuitive. Right? But even though the values are not symmetrical, because there's a zero-sum game, we can do this. So, let's go construct our equations. Okay, so first we're going to do it for player B. Now recall, the top right are the values for player B. So we're not going to use those values. We're going to construct player B's values looking at player A's numbers. Okay? And we do that here. So we're going to take theta 2-1 and theta 2-2. These are the two variables for B. All right? And these represent how often B is going to play the left strategy versus the right strategy. All right? These are the things we want to know. All right? We want to know how often to play this versus that strategy. And this equation is going to tell us to do that. So we're going to take theta 2-1 and multiply it against A's value. Plus theta 2-2, and we're going to multiply that against, again, player A's value. So we're going to get here theta 2-1 times 1 plus 2 times theta 2-2. So theta 2-2 times 2. Okay? That is the left and right strategy. The next step is to apply theta 2-1 and theta 2-2 to the other two sets of values of player A. So it's going to be 2 theta 2-1, because here we're going to have theta 2-1 times 2, plus theta 2-2 times 0. I'm actually going to get rid of these because I think these are confusing and not helpful. So these are the two formula. Now to solve the equation, we make them equal to each other. So we're going to take this here and put this formula here into this part of the equation, and this formula here into this equation, and we're going to end up with theta 2-1 plus 2 theta 2-2 is equal to 2 theta 2-1 plus 0 theta 2-2. Now remember, we can replace these with x and y. It'll make it a lot easier to understand. but I want you to see it as it was intended in the beginning. Now, do you remember the pizza rule? Right? Do not forget the pizza rule. The pizza rule is the whole pizza is your part of the pizza plus my part of the pizza. Okay? And so we can break that down into your part of the pizza is equal to the whole pizza minus my part of the pizza. And we need this because we cannot solve an equation with two variables. We have two variables, theta 2,1 and theta 2,2. We need to get rid of one of them. And we're going to do that by substitution, and the pizza rule helps us do that. Okay? And remember, it's theta 2,2 plus theta 2,1 is equal to one whole pizza. But we can move the variables around to create this construct where we put all the values on one side so we can isolate theta 2,2. So let's go do that. Let's replace every instance of theta 2,2 with 1 minus theta 2,1. So let's go back to this equation here. We have theta 2,1 plus, we're going to substitute theta 2,2 with 1 minus theta 2,1 equals 2 times theta 2,1, and of course 0 times theta 2,2 is equal to 0. So we don't even have to substitute that. Now we have to multiply 2 into the bracket, so that's 2 times 1 is 2, 2 times minus theta 2,1 is 2 times is minus 2 theta 2,1. So it's going to be theta 2,1 plus 2 minus 2 theta 2,1 is equal to 2 theta 2,1. Now, the shortcut, of course, is moving terms on different sides of the equation, but what you're really doing is adding or subtracting on a given side, and you're doing it to both sides at the same time, and that's going to cause some of the terms to cancel out. And what you're going to end up with is 2 is equal to 3 theta 2,1, and then we divide both sides by 3, and we're going to end up with 2 over 3 is equal to theta 2,1. What does that mean? It means, first of all, that when we apply the pizza rule, we can see that theta 2,2 is equal to 1 minus theta 2,1. We know that theta 2,1 is 2/3. 1 minus 2/3 is 1/3. So we know that theta 2,1 is going to be 2/3, and theta 2,2 is going to be 1/3. Still, what does that tell us? It tells us that for player B, to make player A indifferent between their choices, player B has to randomly play theta 2,1 2/3 of the time and randomly play theta 2,2 1/3 of the time. If player B deviates at all from that randomized pattern, they can be exploited by player A and do worse. There's a theorem that shows this is the most efficient way to achieve a positive outcome for player B, so long as player B does not have a spy in the camp of player A telling player B what player A is going to do. And there is a mathematical proof that deductively shows this to be true. So this is how you win the game. And if you don't roll the dice, if you play a hunch, if you play your favorite number, if you look at the stars and are inspired to deviate from randomness, and player A finds out, they will exploit you and you will do worse. This means that when you're gambling with people's lives, when you're launching nuclear weapons, when you're planning wars, when you're sending your submarine out to sea, when you're figuring out the search pattern for your ships, when you're attacking targets with artillery, you have to truly, sincerely, genuinely randomize. And if you don't, you're going to lose. But you can imagine, policy-wise, you could never publicly admit that this is what you're doing. That would be crazy, right? Soldiers randomizing their behavior. But this is the fundamental underlying nature of reality. And it's very often not intuitive and it's not realized. But we make these types of decisions every day, and the ones that do the best are the ones that play according to these rules. So let's now apply the same math to the other side. Okay, let's solve for player A. Okay, should not be too difficult. Again, player A is not going to look at their own values. They're going to use the values of player B. And as counterintuitive as that is, there's a proof for it. You can't fight physics, and you can't fight nature, and you can't fight the fundamental vocabulary of nature. All right, so for player A's got two variables, theta 1,1 and theta 1,2, and player A is going to be applying these two variables to the two values of player B. So we're going to have theta 1,1 times 2, so that's 2 theta 1, 1 plus theta 1, 2 times 1 plus theta 1, 2 times 1. So that's going to stay the same. And then we're going to reapply to the other sets of values of player B. So it's going to be theta 1, 1 times 1, theta 1, 1 times 1, plus theta 1, 2 times 3, 3 theta 1, 2. And so we take these and we build an equation out of the two formula. So we have 2 theta 1, 1 plus theta 1, 2 equals theta 1, 1 plus 3 theta 1, 2, and there's our equation. All we have to do is solve it, and again, we're going to use the pizza rule because we've got two variables here, and we can't solve an equation with two variables. One of them needs to be substituted out. Okay, so here is how we're going to do it. We're going to substitute out theta 1, 2. Okay, so I'm going to reverse the, I'm going to put this here like this. I'm going to reverse the two equations here. So we're going to have 2 theta 1, 1 plus 1 minus theta 1, 1, because we're using the pizza rule. Here we're not using theta 2, 2. We're going to use theta 1, 2 is equal to theta 1, 1. So we're going to modify the pizza rule here for the other player. And this is equal to theta 1, 1 plus 3, open bracket, 1 minus theta 1, 1. And we carry that down to the next level. It's going to be theta 1, 1. We multiply into the brackets. So it's going to be plus 3 minus 3 theta 1, 1 is equal to 2 theta 1, 1 minus theta 1, 1 is equal to theta 1, 1 plus 1. Right? We're going to multiply 1 into the brackets. And this is going to work its way out to theta 1, 1 plus 1 is equal to 3 minus 2 theta 1, 1. This is going to end up being 2 is equal to 3 theta 1, 1. And it's going to end up being 2 over 3 is equal to theta 1, 1. So what does that mean? Well, it means that theta 1, 1 is going to be evaluated as 2 over 3. And so by the pizza rule, theta 1, 2 is equal to 1 minus 2/3. So theta 1, 2 is going to be 1/3. Now, these values are, they look symmetrical. Player A's got a 2/3, 1/3 split, and player B also has a 2/3, 1/3 split, but that's not always true. In some of the formulations of this, I have a 1/4 and 3/4. So there's no automatic dependence between the two players in terms of the proportion of these different strategies that they have to play. So you can see here, player B has their optimal strategy, and player A has their optimal strategy, and only by playing these optimal strategies will they maximize their outcome. Any deviation from this will result in possible exploitation by the other party member. So this might be very, very counterintuitive, but it's essential that whenever two sides are fighting each other under circumstances of uncertainty, that you're going to have choices that are difficult to make because they depend on the choice of the opponent and you're not sure what the opponent's going to do. This approach provides the optimal solution to winning under those circumstances. So that's the solution for the mixed game strategy. So the implication of the mixed game strategy is that Nash proved that it's the most efficient way of an individual player getting the maximum utility they can from their choices. The mixed game strategy is also the Nash equilibrium. It tells us what the outcome is going to be in a game. Now you can expand this game to have more strategies. You can actually have more cells that are mixed game, not simply with two variables, although it becomes unwieldy with the pizza rule. You can have more players. You can extend that from a 2-player to a 3-player game by creating a 3-dimensional cube. You can have a 4th-dimensional element to the cube, although it can't be represented and visualized. Now, of course, there's a difficult public policy implication, which is when you use nuclear weapons and you have any form of cycling because you don't have a dominant strategy, which is very certain when you've got two sides challenging each other, then you need to roll dice and embrace a random method to choose your strategy. We come from a culture which celebrates the application of the intellect. So we have this image in our head of Napoleon who sits down at Wagram on a chair around a fire and thinks about how to fight the battle. And then the next day, Napoleon's brilliance emerges and he completely defeats his opponents. That doesn't exist. It's a myth. If you are a wise commander, you will embrace the mixed game strategy and understand that when you're dealing with an opponent, to win, you have to gamble on people's lives with dice.